In this video, I'm going to be going over some of the Baldwin rules. And I think this first example here is a good explanation as to how we're going to use them. So if we didn't have these Baldwin rules, we wouldn't know, for example, if the product on the right is going to be favored, or if the product on the left is going to be favored. We also wouldn't have a way to really distinguish verbally or with terminology how we're going to describe these. But Baldwin has a nice table that allows us to come up with some nice names and some nice explanations as to if one will be more favored or not. So let me pull up that chart real quick. So these numbers are going to represent our atoms. And I'll talk a little bit more about that in a minute. We're going to call this left side anything that is endo. And this right side will be our exo. Right. So what is endo and what is exo, according to Baldwin? Well, I like to think of endo and exo as being the location of where our lone pair of electrons turns up in the end. So just real quick, I guess we could do this for fun. If we wanted to get the stuff on the left, so this orange product, we'd move these lone pairs of electrons from this nitrogen to this oxygen, and the oxygen will end up getting some electrons back from doing that. Now over here in orange, the oxygen's not part of the ring. It's kind of hanging out, like you could almost think of it as a substituent. So it's hanging out and it's outside, and so that would be an example of something that was exo, where the electrons that are being pushed out of the way are on the outside. So I'll talk more on that in a little bit, but Baldwin also goes on to describe, are we dealing with something that's a single bond? So something that's a single bond, and he called those tet. So tet. And then I guess the next intuitive kind of bond would be the double bonds. And that would be an example of what I have just shown in, with the mechanism right above. And Baldwin called those trig. And the last one is dig, and you guessed it, those are going to be triple bonds. So the names tet, trig, and dig come from the actual bond angles that are made when trying to form these rings. Anyways, Baldwin has more to offer in this little chart that we're making right here. And he says that if you're dealing with anything that's tet, so again, like single bonds, and you're trying to do something that is endo, well, good luck, because he says 3 through 7, so atoms or cyclization that requires 3 through 7 atoms are going just to be very slow and hard to do. So he kind of tells you good luck trying to get that to work, because it's not going to go very easily. He also says that for the trig section, while also an endo, 3 through 5 will be difficult to do. And so what that leaves us with in the endo section is the 6 through 7 for trig, and 3, 4, 5, 6, and 7 for the dig. Over in the exo portion, it's a little bit more generous about what we're allowed to do. The only thing we're going to see crossed out is the 4 and 3 in the dig section. And so we see we're a little bit more limited in the endo, but nevertheless, we can still use this chart to figure out what's going on, and we can also name some things. So if we, since we already have this mechanism in white for the orange, we might as well classify it now, because we can now name it with this chart. So if we wanted to name what kind of cyclization this was, we should start by counting the size of the ring, and we can either do that by knowing the product, because I've written it over here, or we can just count like we would traditionally. So if we made the nitrogen be 1, this blue dot is 2, 3, 4, 5, and this carbonyl is the 6th. And so we're dealing with stuff that is going to be 6, so anything that has 6s in it. We need to narrow this down because when we attack that carbonyl, the electrons will be thrown onto the oxygen. The oxygen, we said, is kind of hanging outside of our ring here, and so that would be something that is exo. So we are dealing with the exo category here. Now that double bond, so the carbon to the oxygen, that carbonyl is a double bond. So we're dealing with something that is trig. So we are in this region right here. So if we wanted to name this, we would say it was a 6-exo trig cyclization going on. Now over here on the right in pink, we have, again, we could probably guess it's going to be 6 carbons, but let's go ahead and count. Get a good color. So here would be the second carbon if nitrogen is the first atom. There's 3, 4, 5, and the mechanism would be a little bit different. We're going to attack the beta position. And when you attack the beta position, you're going to give that alpha carbon its electrons. Now that alpha carbon actually is part of your ring. That goes into making the 6-member ring. And so that will be an endo product that we're making. And so again, we are dealing with something that is 6 carbons. And I didn't say what the 6 is, but there's the 6. It's that beta carbon. We're dealing with something that's 6 carbons. Since it's the electrons that are going to be moved out of the way are part of the ring, we're going to say this is endo. So something that is 6 endo. And again, we are dealing with a double bond. So this will be a 6 endo trig. And we can find that right there. Now, which one is going to be your major product and which one is going to be your minor product? Well, in this case, Baldwin isn't actually too useful. Both the 6 endo trig and the 6 exo trig are okay. We can do both of them here just fine according to Baldwin. The issue is, it's actually not really an issue, but the small caveat to this is that what's going to be easier? Going back to organic chemistry 1, what's going to be easier, attacking a beta position or a 1,2 position with something that's an amine? Well, if you remember that amines are just like alcohols, and attacking 1,2 direct is going to be slower and less likely than attacking a conjugate. So doing something that's a conjugate addition or 1,4. And that would be attacking the beta position. So the one that shows the beta position is the one in pink. And so that one is going to be our faster reaction. And this one will be our slower one. So a lot to take in. Let's go on and try the second one and try to put all the pieces together. So here in this second example, all I've done is just taken out 1 carbon from that turquoise molecule in the middle. And we're going to use this same chart to name it and determine which one's going to be our major product, and really which one's going to be formed fastest. So in the pink, we have, well, this mechanism going on. So electrons from this nitrogen look to have attacked the beta position. Okay, and then it bumped electrons up to that carbon. It formed a 5-member ring. You could also figure that out by counting. So there should be 4 purple dots. So there's the 4 purple dots, and the nitrogen makes the 5th atom. And that's what formed our molecule in pink. I'm going to go over this mechanism real quick in pink. Now the mechanism in blue would be a little bit different, or I'm sorry, the mechanism in orange would be a little bit different. It would go and attack the carbonyl, and the carbonyl would then get the electrons. If we're counting atoms, this would be the 2nd atom, 3rd, 4th, and the 5th atom in green. Okay, so we know if we're doing the orange product or the pink product, we're dealing with something that's going to be 5 atoms. So now looking at the orange, let's go ahead and try naming it. So the orange mechanism shows that the electrons are coming over to this carbonyl. It hits the carbonyl, and then the oxygen gets the electrons. Well, in this case, the oxygen looks to be on the outside. So since it's on the outside, we're going to let it be exo. So Uh, in the exo category, here's 5 carbons and it is at trig. So we are dealing with something right here. So naming that would be 5-exo trig. And it is allowed. So over in pink, again, we have 5 carbons. Following the pink mechanism, when it hits that beta position, the electrons will be pushed onto this alpha carbon, and the alpha carbon's part of our ring, and so we're going to call that endo. And so where is 5? So 5 trig, so 5 with a double bond, and when it's endo would be right there. Now that's crossed out according to Baldwin. That's not a very good suggestion. It's actually forbidden, he says. And so naming this, first of all, it'd be 5 endo trig. And now determining which one's going to be fastest and which one's going to be slowest. Well, since we know the 5 endo trig is a forbidden cyclization according to Baldwin, this one's going to be very slow if you get any to form at all. This one, however, is going to be the fastest, and you'll see the most product from it. You might see closer to about 100%. You might see less than 1% of the stuff on the right in pink. So this kind of shows you that although the one on the left wasn't a beta attack, so it wasn't a conjugate addition of the amine like in the other problem, but it was faster here. So it all depends on this chart.